Hello and welcome back to the Biochemistry for Health Sciences channel. In the last video, we introduced hyperbolic and sigmoidal curves. In today's video, we will try to explain hyperbolic and sigmoidal curves in terms of a concept that we call cooperativity. So what's the relationship between cooperativity, hyperbolic, and sigmoidal curves? There is a number that we call n, which is called the Hill coefficient, and this number, Hill coefficient, measures the cooperativity of the binding of a ligand, such as a substrate molecule, to the enzyme. So here are four curves. You can see for the hyperbolic curve, this value of n, this Hill coefficient, is 1. For the remaining curves, the value is greater than 1. So for the hyperbolic curve, n is 1. For the other three curves, the red one has an n value of 1.5, the green has an n value of 3, and the purple one has an n value of 6. So we say that these curves that have a positive n value greater than 1, they are showing what we call as positive cooperativity, and these are seen as sigmoidal curves. Note that all of these curves have the same Vmax, in this case 100 millimolar per minute, and all of these curves have the same Km or K 0.5, which is, in this example, 10 millimolar. Notice that as n increases from 1 to 1.5, as shown in the red curve, you can see the blue curve is slowly becoming sigmoidal, and you can see a little sort of S developing here. As the n number increases to the green curve where n is 3, you can see the delay. You can see a much better S here developing. And as n increases even further to 6 in this example, you can see nothing is happening, not much is happening at low substrate concentration, and then you see this S developing much better. So the value of n basically measures how much of this S behavior that we see in this curve. In other words, how much is the enzyme showing this cooperativity effect. The general equation of all of these curves is shown here. V equals Vmax times S to the power of n divided by K to the power of n plus S to the power of n. In case of the hyperbolic curve where n equals 1, if n equals 1, this equation basically comes out to be V equals Vmax S divided by Km plus S. So this K here, we call it a special name, Michaelis constant, or Km plus S. If n is 1.5, then these numbers here, these powers will all be 1.5. If n is 6, then these powers here will be 6. So this means the difference between a hyperbolic curve and all the sigmoidal curves is really in this value of n that measures the amount of cooperativity that the enzyme is showing. So let's see what is this cooperativity and what kind of enzymes may show hyperbolic curves and what kind of enzymes may show sigmoidal curves. So in the first case, here is an enzyme that has only one binding site for the substrate molecule. So in this case, there is no cooperativity, and therefore this curve is going to be hyperbolic. In the second case, once again, there's only one binding site for the substrate. However, this enzyme does show cooperativity. Now, this is a very rare case. It's something very new that has been discovered. A good example is the enzyme glucokinase. It has only one polypeptide chain. We say one subunit or one monomer. It has only one binding site for the substrate. The substrate is glucose, but it shows a sigmoidal curve with increasing glucose concentrations. So once again, this is a very rare situation. In case number 3, the enzyme has 2 or more subunits. That means there's one binding site for the substrate here, there could be another binding site for substrate here, and it could be another binding site for substrate, so there could be 2 or more binding sites for the substrate. In this case, for these type of enzymes, you could have a cooperative effect showing sigmoidal curves, or they may not show cooperative effects. In that case, you get hyperbolic curves. Since this ligand here, substrate, and this ligand here, substrate, is the same ligand, we say the interactions between these two, these are homotropic interactions. So the interactions between these two ligands on the enzyme, these are homotropic interactions, the same ligand. In this fourth example here, we have an enzyme, once again, with only one binding site for the substrate, but it also has another binding site for molecules that we call activators or inhibitors. So in this case, because there's only one binding site for substrate, we will not see cooperativity. So you will have the hyperbolic curve. However, this binding of the substrate to this enzyme can be altered by the presence of the activator A or the inhibitor I. So this is what we call allosteric control of the enzyme. So in this case, the interaction between AI and the enzyme and the interaction between substrate and the enzyme, these interactions are heterotropic interactions because the substrate is different from A or I. And in the last case, we once again have an enzyme with 2 or more binding sites, as well as binding sites for A and I. So in this case, there may be cooperativity between the substrate molecules. So in that case, you will see sigmoidal, or there may not be any cooperativity. In that case, you see hyperbolic. And once again, the presence of this A and I will control or can affect the binding of the substrate to the enzyme, the allosteric control. So how do we go about determining this number and the Hill coefficient so that we can understand how much cooperativity is going on in an enzyme, if any at all? This idea of cooperativity was actually first introduced for hemoglobin. So remember, for these oxygen binding proteins, we had this equation. Now for enzyme kinetics, we have this general equation for the curves. Just as we rearrange this equation into this so that we can make the curve into a straight line, we can do the same thing here for enzyme kinetics. We can take the equation for the curve, rearrange it so that we get an equation for a straight line. And if we do that, we can determine the value of n. So here we plot log v divided by v max minus v. So this is our y. And on the x-axis, we plot log s. So this is log s on the x-axis. And when we do that, we get a straight line. And if we find the equation of the straight line, the slope n, in this case the slope is 3. This 3 is the Hill coefficient or n. Okay, so that's how we can easily determine the value of n, the Hill coefficient. So if n is 1, there is no cooperativity, and we get the hyperbolic curve. If n is greater than 1, then we get positive cooperativity, and we get a sigmoidal curve. And if n is less than 1, then we get negative cooperativity. And here's a curve that shows you negative cooperativity. So to summarize, cooperativity is also seen in enzymes, just like in case of hemoglobin. So when one substrate binds to a binding site, that can change the conformation or the shape of the other subunit, and the second binding site may be better, might get a higher affinity to bind the substrate. So the substrate binds the second binding site even easier. In that case, we will have positive cooperativity. However, if the second site changes such that the second substrate molecule has a lower affinity for the binding, then we'll have negative cooperativity. It also should be remembered that just because the enzyme has multiple binding sites for the substrate, we don't necessarily have to have any cooperativity at all. So enzymes that have multiple binding sites may or may not show cooperativity, and therefore demonstrate either sigmoidal curves or hyperbolic curves. We will have more videos on this complex but important area of enzyme kinetics in the near future. Until then, goodbye and have a wonderful day. See you in the next video.